In this lesson, we are going to carry on with probability distributions, specific ones. In particular, we're going to look at something called a geometric probability distribution. We've already looked at uniform probability distributions and binomial probability distributions, which are each specific types of probability distribution. So here's another one. So in some board games, you cannot move forward until you roll a specific number, right? It's been a while since I played them, but I'm thinking of games like maybe Sorry. So you have to roll, in this case, I'm thinking ahead, I might have to roll doubles, for example, to move forward, which could take several tries. Sorry, I never finished that sentence. Which could take several tries. Manufacturers of products such as switches, relays, and hard drives, just to change direction a bit here, need to know how many operations their product can perform before failing. So it's good to know, imagine you're a manufacturer, it's good to know how long your product is going to last in general before it fails. In each of these situations, the critical quantity is the wait time or waiting period. In other words, the number of trials before a specific outcome happens. So just wrap your head around that for a second. So in terms of the game, how many times do you have to roll before you get your doubles or get whatever that number is before you're allowed to move? In terms of the production company, how many days or months or years go by before your switch fails or your battery dies or whatever? How many times can you start the car before your battery dies? So it's the wait time. Wait time is the number of times something can occur before it changes, all right? The probability distribution of an infinite number of trials is... Sorry, phone ringing. The probability distribution of an infinite number of independent trials, where each trial has only two outcomes, is called a geometric distribution. The random variable is the number of unsuccessful outcomes before success occurs. So we've got, again, independent trials, but in this case, unlike binomial distribution, where we had a set number of trials, and that was our n, we haven't set a limit on how many trials there can be. We just keep going until whatever it is we're measuring changes, right? So that's where the infinite number comes from. So in theory, again, if I made a relay switch for a construction company, in theory, this switch could last forever. Now, obviously, nothing lasts forever, but I don't know how long it's going to last, so we start off with the assumption that it's going to go on forever and then just wait and see. So each trial has only two possible outcomes. We've seen that already with binomial distributions. We can call them success or failure. And again, this is called a geometric distribution. That's the title of this lesson. The random variable is the number of unsuccessful, I think it's good to underline that, outcomes before success occurs. The random variable is the number of unsuccessful outcomes before success occurs. So, let's look at an example to make it clearer. To get out of jail in Monopoly, you have to roll doubles. Calculate the probability distribution of getting out of jail in X number of rolls, graph the distribution. All right, so remember X, my random variable, means how many times do I, in this case, how many times do I not roll doubles before I do roll doubles? So picture the situation, you're playing Monopoly, your character, your token is in jail, and you pick up the die, and let's say you get doubles on the very first roll. That's lucky, you feel good. That would be an X value of 0. In other words, you were unsuccessful 0 times, and then were successful on the first try. What's the probability of that happening? Well, I've already drawn my table over here just to save a little time for all the outcomes for rolling 2 die. We've talked about this before. So rolling doubles would be rolling a 1 and a 1, a 2 and a 2, a 3 and a 3, 4 and a 4, 5 and a 5, or 6 and a 6. If we want to think of that in terms of P and Q, because we've already called P the probability of success back in our lesson on binomial distributions. The probability of success of rolling doubles would be the 6 possible doubles out of the 36 trials. That reduces to 1 over 6. And if we think of Q as failure, then, it's 30 over 36, or 1 minus P. Let's write it that way, actually. 1 minus P, because they have to add up to 100%. So 1 minus 1/6, which equals 5/6. Okay, so what's the probability of rolling doubles on our very first try? So one trial, the probability is going to be 1/6. Let's move on to the next one. What's the probability of first not rolling doubles and then rolling doubles? Well, the probability of not rolling doubles we've already seen is 5/6. So first we have to not roll doubles, and then, and meaning multiply, we've learned that, and we've talked about this many times before, and then I have to roll doubles where I have a 1/6 probability of that happening. Maybe I should be changing this to decimals as I go along. So 1/6 is 0.16 repeating, and 5/6 times 1/6 is going to be 0.138 repeating. Okay, so we've got the first two probabilities there. What's the probability of being unsuccessful twice and then being successful? Well, 5/6 probability on the first roll, then we're unsuccessful again, another 5/6 probability, and then finally on the third roll we're successful. So really, if you look at that, I could rewrite this as 5/6 squared times 1/6. But I won't write that like that right now. Anyway, what that works out to is 0.1157, approximately. I've rounded. And then if I want to have 3 unsuccessful rolls and then get a success, then we've got 5/6 for the first roll for being unsuccessful, another 5/6 for the second roll being unsuccessful, another 5/6 for the third roll. Finally, we've got our success, which is 1/6, and that works out to be 0.0965. And again, we could simplify that, couldn't we? We could rewrite that 5 over 6 times itself 3 times is just 5/6 to the 3. So you can start to see a pattern forming. In fact, I'll use that pattern for the next one. If I want to have 4 unsuccessful rolls, then I could just write that as 5/6 to the exponent 4 rather than writing out 5/6 times 5/6 times 5/6 times 5/6. Then we still have to have that 1/6 probability of having a successful roll. 0.0804. 5/6 to the 5, right? The pattern has been established. Hopefully it's easy to see now. 0.06698, or 6, let's undo that. 0.66670, I'll round to 4 decimals. Okay, we got one more, 5/6 to the 6 times 1/6. 0.0558, etc. All right, so calculate the probability distribution. There we have it for the first 6. We don't have to stop. That's why it says etc. here, right? There could be 7 unsuccessful rolls before we get a doubles. There could be 8. There could be 9. There could be 100. In theory, we might never be successful. We might never hit a hit a doubles. But it gets less and less likely. If we look at the probabilities, they start out at 0.16 repeating, and they go down from there. So actually, for any single outcome, if I had to predict what my best probability is for any, someone asked me, how many times do you think you're going to roll before you roll doubles? My highest probability for picking any one number would be 0. It's not great. It's still only 17%, but it's better than any other single one after it, right? So it just goes down, keeps going down. So it keeps going on forever, in theory. So our histogram, let's see, don't have, the way this one's divided up, I'm going to set it up a little differently. I'm going to set it up as 0, 1, 2, 3, 4, 5, 6. Yeah, I'm going to have to start here. 0, 1, 2, 3, 4, 5, 6, and know that it keeps going from there. And again, my histogram is just going to be bars, and it's going to be the height is going to be p at x, the probability of a particular outcome occurring. And so 0.16 repeating would be about here. And then 0.138, maybe I'll just draw the lines across here. 138 repeating would be about here. And 0.11, let's call it 0.115. About here. Actually, maybe it is easier just to draw my bars down. It makes me see what's going on better. And then 0.096. And then 0.08, let's call that one. And then 0.067, whoops. And then 0.055. Okay, so there's our histogram so far. But that's not it. There's more. There's more to this histogram. It's going to, we could have 7, we could have 8 for our value of x. And so, just to make that clear, let's do 7. If x equals 7, I got p at x equals 0.0465. And if x equals 8, just to do one more, p at x is going to equal 0.0388. So for 7, it would be a bar about here. For 8, it would be a bar about here. And so we can see that it's sort of going like this. Now I'm just estimating, obviously, here, but what you'll notice is it just sort of tails off. In addition, the gaps between successive outcomes are getting smaller. So these little gaps that I'm drawing here are getting smaller, so they're getting closer and closer to each other, right? Obviously, at some point, they have to get very close to 0 because the entire area under this curve has to equal 1. The probability of all these bars, even the infinite number of bars, has to equal 1. Let's look at the expected value. So E at x, let's write that a little neater. Make this bigger too. No, I guess I have to zoom out so I can see my values. All right, E at x equals 0 times, let's just call it 1/6, plus 1 times 0.138 repeating, plus 2 times 0.116. I'm going to round to 3 decimal places at this point, just to keep it smaller. Plus 3 times 0.010. No, yeah, 3 decimal places. 0.97 plus 4 times 0.080 plus 5 times 0.067, and I'm just going to stop at the original 6 I did, plus 6 times 0.056. Okay, I am going to have to type all this in my calculator. So 0.13888. I skipped the first term since it was just times 0, plus 2 times 0.116, plus 3 times 0.097, plus 4 times 0.08, plus 5 times 0.067, plus 6 times 0.056. I got 1.652888. But again, this is not the entire distribution because it's an infinite distribution. So definitely I should be rounding this. Maybe I'd round it to 1.7 even, because I know it's going to go, I don't know if it's going to go up or down actually. I should take that back. All right, I'll go to 2 decimal places for now. So that's my expected value. What does that mean? It means that if you were to play a whole bunch of games of Monopoly where you're in jail a whole bunch of times, on average you can expect to have to roll 1 to 2 times, somewhere between 1 and 2 times, before you then hit your doubles. Okay? So probability in a geometric distribution. The probability of success after a wait time of X failures is given by this formula here. So we've pretty much established that in our table. We saw what happened if Q is our probability of failure, then we do Q to the X, where X is the number of failures we have, just times the probability of success. And then we have a formula for the expected value as well. Again, I used the expected value, the general expected value formula to calculate up above, but there is a shortcut. The expected value of a geometric distribution is the sum of an infinite series, which obviously we can't calculate directly because it's infinite. However, it converges. In other words, it gets close. Whoops, that was supposed to be a highlighter. It converges to the simple formula Q divided by P. So if I want to check that, then I can use that formula here, and I would have E at X equals, what was it, 5 over 6? That's Q, divided by 1 over 6, which equals 5 over 6 times 6 over 1. What have I done wrong here? 5 over 6 divided by P, which is 1 over 6. I'm not getting what I expected, so I'm just going to backtrack and do it a little more slowly. So, E at X equals 5 over 6 divided by P, which is 1 over 6. So 5 over 6 times 6 over 1, which equals 5. Well, I didn't pre-calculate out what my expected value was using the other formula, so it's possible I made a mistake there. 5, that definitely, I don't see anything wrong with what I've done there. Here, you're going to get a chance to see me troubleshoot. What has gone wrong? Let me just double check my numbers that I did in blue here. 0.13888 times, plus 2 times 0.116 plus 3 times 0.097 plus 4 times 0.08 plus 5 times 0.067 plus 6 times 0.056, getting the same answer. It's going to keep going up. So if I were to add, let me add the other ones in there, plus, so 1.65 plus 7 times 0.0465 plus 8 times 0.0388. Now it's gone up to 2. Okay. So when I added extra ones on there, when I added x equals 7, let's just add those on here now, plus 7 times 0.0465 plus 8 times 0.039, what I got was 2.29. So that's a big difference, just adding those other ones on there. So I guess the takeaway from this is that if you look at these bars here, obviously there's quite a bit of still more of area to be added on to this. So only doing 6 was a problem. And if we keep adding these other ones on, it's going to keep rising. 5 would be the one that we would predict, though. I'm going to go with this one here because it's the basic formula. It's what we would expect. Okay, let's look at some other examples. Kawhi has a success rate of 86% for scoring free throws in basketball. What's the expected wait time before he misses a basket on a free throw? All right, so expected wait time, there's our E at x, is Q divided by P, where he's going to miss before he misses a free throw. So we have to be careful on our wording here. So I just want to make sure I've wrapped my head around this. So in this case, missing a free throw would be success. In other words, that's what we're looking for. So P in this case would be 1 minus 0.86. We're looking to see how many successes he has or how many baskets he sinks before he misses one. So sinking a basket is our 0.86, and missing the basket is the 0.14. So 0.86 divided by 0.14 equals 6.14. We would expect him to sink about 6 baskets before missing one. Suppose that an intersection you pass on your way to school has traffic light that is green for 40 seconds and red for 60 seconds. What is the probability that the light will be green when you reach the intersection at least once a week in 5 days? Okay, now we've given 5 days. This is not an infinite sequence anymore. That means this is not geometric. This is binomial, right? We've got a set number of trials, 5 trials. Not binomials, binomial. N equals 5. At least once, well, that's telling me indirect method probably, or at least 1, 2, 3, 4, 5 times. It could be green up to 1 to 5 times. I could calculate all those and add them together, or I could do the indirect method, where I could do probability of getting 0. Sorry, probability of it, let me change that. Probability of at least 1 green is going to be 1 minus the probability of getting 0, right? Let's call that P at 0. So that becomes 1 minus NC x, so n is 5, so 5 choose 0. What's the probability of getting a green? Well, if it's green for 40 seconds and red for 60, then it's 40 over 100, because 40 plus 60 is 100. So we got a 0.4 probability of success, getting a green. We've got a 0.6 probability of failure, getting a red. So that becomes 0.4 to the 0 times 0.6 to the 5. So one minus 0.07776, which is 0.922, or about 92%. So you got a strong probability of getting at least one green light. B part, what is the expected number of days before the light is green when you reach the intersection? Okay, now we don't have a set number of trials. We switched out of binomial mode into geometric mode. So we have an infinite series. So geometric. So what we then have is back to E at x equals q divided by p, which is going to be, what was it, 0.6 divided by 0.4, which equals 1.5 days. So somewhere between 1 and 2 days. And that makes sense because it's green almost half the time. Yes, it's less than half the time, but it's almost half the time. We wouldn't expect that we'd have to wait that long to catch a green one. And that's it for this lesson.